so you can kind of like the equator is flung out a little bit by Earth's rotation. It's not nearly as big as indicated here. You can't really just look at the Earth and tell it's bulging at the equator, although, as we'll see, for Jupiter and Saturn, you can. It's obvious for Jupiter and Saturn. The fact that Earth is bulging at its equator and is tilted in its orbit around the sun means that the moon's gravity and the sun's gravity pull on that bulge and try to turn the Earth right side up, just like Earth's gravity tries to tip my model Earth right side up. And the fact that the real Earth is spinning causes the attempt to tip it right side up instead to cause it to precess. So Earth's axis of rotation precesses around like a top, and so the direction that it is pointing in space traces out a circle on the celestial sphere. Like if my arm is the axis of rotation and I'm precessing around here, if the direction of the axis is precessing around, notice that I would be drawing a circle on the celestial sphere. And what that means is where the north celestial pole isn't constant. It's almost true that Earth's direction of rotation stays constant as we move around the sun, which gives us the seasons and all that. But the direction isn't exactly constant. With a period of about 26,000 years, it's precessing. So in any one year, it hardly changes at all because it's just 1/26,000th of a complete cycle. But nevertheless, it is changing. And what that means is Polaris, the North Star, isn't always the North Star. We just happen to be living in a time when our direction of rotation is pointed at very nearly at Polaris, but that certainly isn't always true. In 15,000 years, the bright star Vega will be the bright star that's closest to the celestial pole. When the pyramids were built in ancient Egypt, like 5,500 years ago, a star called Thuban in the constellation Draco was the North Star. It changes over time. Here's another illustration of that idea. This is the circle that the North celestial pole moves on over the course of the precession cycle. So we just happen to be living in a time when Polaris is a good North Star, but that's not always the case. And that's what precession does. And we call it precession of the equinoxes because remember that the celestial equator intersects the ecliptic at the 2 points that we call the equinoxes. But the celestial equator is 90 degrees from the two celestial poles. So if the celestial poles are moving around on the sky, so is the celestial equator. And therefore, so is where the celestial equator intersects the ecliptic. So the equinoxes on the celestial sphere, along with the solstices, also are moving on the sky slowly. Right now, the spring equinox is in the constellation Pisces, but it hasn't always been. And in fact, the ancient name for the vernal equinox, the March equinox, is the first point of Aries. And that's because in ancient times, the March equinox was in the constellation Aries instead of the constellation Pisces like it is now. In the future, it will be in the constellation Aquarius, which is why if you've ever heard, there's a 1968 musical called Hair, and there's a song called The Age of Aquarius in it. They're talking about the vernal equinox, the spring equinox, the March equinox moving into Aquarius, which some astrologers consider to already be happening. According to the arbitrary astronomical definitions, that won't happen until about year 2600, but it's not going to make any difference, because astrology is just nonsense. But one thing that's interesting to know is that what astrologers decided to do is keep the signs fixed, even though precession is happening. They kept the boundaries of the astrological signs fixed to the location of the March equinox, which means for most people, the sun is actually in the next constellation over on the ecliptic from the one that your astrological sign is named after. Most people, if you look up where the sun is on the celestial sphere on your birthday, it's not in your constellation, it's in the next one over. And that's because of precession. And that's just one more reason why astrology is kind of silly, because if you're a Leo, most likely the sun was not in Leo on the day that you were born, because they decided to not account for precession.
So cause of it is the bulge,
Yeah, the Earth's equatorial bulge. The Earth bulges out at its equator because of the fact that it's spinning. And that means that the sun and the moon pull a little bit harder on the near side of the Earth to them than they do on the far side of the Earth to them. And so if you kind of think of that here, if you think of these arrows here, that represents the gravitational pull of the moon and the sun on the equatorial bulge. If you imagine pulling on strings there, that would be trying to tip the Earth up. It would try the pulling on the bulge is kind of trying to make the Earth stop being tilted. But it's spinning, which means instead of stopping being tilted, it just stays tilted, but the direction that it's spinning moves around. And that's the precession. What it means is Earth acts like a top, or even, excuse me, fancier way to put it is it acts like a gyroscope. Yes?
So precession is just like essentially wobble?
If you like, yeah. Yeah, but it's not like, just like wobbling, it's very regular. It has a very distinctive pattern to it. But yeah, the Earth's direction of rotation wobbles around every 26,000 years. But the fancy word for it is precesses around every 26,000 years. Yes?
Could you go over the different types of solar eclipses?
Mm-hmm. Solar eclipses. Oh, yeah, pictures there. What's that? What is that?
Oh, my friend drew a solar eclipse.
Oh, okay. Is it suitable for Frankie?
Yeah, I mean.
Okay, all right. Let's get it laminated. Okay. Yeah, so in terms of solar eclipses, you can have, so first of all, overall, most eclipses, unless the moon shadow, unless the moon is pretty far north, unless the moon shadow is passing pretty far north or south on the Earth, so that the center of its shadow in the umbra misses the Earth, but the penumbra might still hit the Earth. In general, most eclipses are either going to be overall called a total eclipse or an annular eclipse. There are some that are combined, where it's annular for part of it and total for other parts of it, but usually it's either total or annular. A total eclipse is when the moon is close enough to us that the tip of the umbra makes it all the way to the surface. Put another way, if the moon is close enough to us, it looks a little bit bigger than the sun in the sky and is able to completely cover it, in which case you get a total eclipse. On the other hand, if the moon's umbral tip passes above the surface of the Earth, the shadow of the moon's, the umbra, doesn't quite touch the surface of the Earth, that'll be because the moon is a little bit too far from us, and it looks a little smaller than the sun in the sky, and so it can't completely cover it, and so we just see a ring of sun around it if we're lucky enough to be in the path of annularity, if you will. So that's one thing. You can get a total eclipse, you can get an annular eclipse. But even so, only lucky people who live right along the path that the umbra passes along, that the tip of the umbra passes along or right over, actually get to see totality or the eclipse becoming annular. What most people see is like what if you stayed here in 2017 when there was a total eclipse visible in parts of America, most people just saw a partial eclipse, because if you're in the area that only the penumbra of the moon covers, you're not in that path of totality, then you just see a partial eclipse in that case. So at any given time, you might see a partial eclipse, a total eclipse, or an annular eclipse. But even if you're going to see a total eclipse, it spends most of its time being a partial eclipse before and a partial eclipse afterwards, as the moon bites out more and more of the sun, so to speak, covers it completely, then starts moving off the sun.
So it depends on if the umbra is touching.
Depends on whether the umbra tip touches Earth's surface or not, if it reaches the ground. And what you see depends on whether or not you put yourself in the path of the total eclipse, or if you stay outside of it, in which case, if you're completely outside, if you're down here for this eclipse, you wouldn't see anything. But if you're like right above, if you're a little above or a little below the path of the total eclipse, the path of totality, you'll just see a partial eclipse, which ain't near as good. I had somebody ask me once, they said they were going to be in Germany back in '99, which is when there was a total eclipse there, and they said, well, where we're living, it's going to get 99% covered. Is that good enough? And I said, no! 99% eclipse is no better than like 1% eclipse. It's just not the same. You've got to have it totally covered for it to really be spectacular.
Is there a time where an eclipse not like happening anymore?
No. Well, I shouldn't say that. So there will eventually be a time when we don't get total eclipses anymore, because the moon is slowly getting further from Earth. We'll talk about that more when we talk about the solar system. The moon is actually slowly getting further from Earth, and at the same time, Earth's rotation is slowing down. But in other words, eventually the moon will be far enough away that there won't be total eclipses anymore, because it will always look smaller than the sun does in the sky, no matter what. So we're lucky enough to be living in a time where we can just barely get total eclipses. But it's actually good, because if the moon was a lot closer to us, it would also cover up most of the corona, and it wouldn't look as good either. So we have a great year. Yes.
Does that mean, like, just out of the picture, does that mean the moon's orbital path is like expanding or changing?
It does, yeah. The moon is getting further away from us every year. Yeah, just a little bit. I forget what the number is. I think it's like a centimeter per year or something like that. But when the moon was formed, it was about 10 times closer to us than it is now. The moon was our best explanation of the formation of the moon is that proto-Earth was hit by a Mars-sized protoplanet in a spectacular collision that tore out a lot of material that coalesced to form the moon, and it formed within about an hour of that collision, and it was about 10 times closer to us than it is now, and then it's slowly been getting further away ever since then. So now if a collision like that happened now, we would literally be toast, but this was proto-Earth, so good for us if the Earth survived the collision and cooled down, and it's all good now. In fact, it's extra good, because it turns out that the moon stabilizes Earth's axial tilt, and without that influence, the tilt would vary a lot, and that would make great amount of change in the seasons, and so that would interfere with evolution of complex life forms. So it may be that, we don't know this for sure, but it may be that only Earth-like planets that have a comparable sized moon can have likely the evolution of intelligent life, because you need something to stabilize the tilt of the planet. So thank you, Moon. Appreciate that. Yes?
This is unrelated to that.
Okay.
Could you talk about how retrograde motion is explained via the modern heliocentric model?
Yeah, the modern heliocentric model. Yeah. So, okay, so first of all, what retrograde motion is, right, is the, so it's not something you see on any given night. And so this is like for Mars. Mars always rises in the east and sets in the west, whether or not it's moving retrograde. Retrograde motion and direct motion refer to how the planet is moving amongst the stars from night to night to night. It's a slow drift, just like the sun's motion along the ecliptic is a slow drift, because it takes a whole year for us to go once around the sun. Similarly, from night to night to night, if you were to photograph or plot the position of Mars on a star map every night, you would see that it's moving amongst the stars, apparently, from Earth. here's where Mars was on November 3rd of 2011. Here's where it was on, I don't know what, but in other words, each one of these is different nights, so just a picture of Mars on different nights. Here's where it was on 23 January 2012, 4 March of 2012, 11 April 2012, 6 July of 2012. So here, Mars, starting with this one, Mars was getting further east on the sky every day. And again, I'm not referring to Mars rising and setting. That's caused by Earth's rotation. What I'm talking about here is caused by the fact that we and Mars are both going around the sun, so that the line of sight from Earth to Mars keeps changing. This is something you'll see only if you plot on a star map from every night. So Mars was moving to the east on the celestial sphere in between before 3 November 2011 all the way through 23 January of 2012. And then after that, it started moving westward amongst the stars. Every night you would see it was a little bit west on the celestial sphere compared to where it was the night before. That continued until 11 April 2012 when it reversed again, so to speak, and started moving east amongst the stars again. So when it's moving eastward, which is most of the time, that's called direct motion. And when it's appearing to move westward, that's called retrograde or backwards motion. So that's what it looks like to us, is that for a while the planet appears to be going backwards amongst the stars compared to what it usually does. But again, you have to realize it doesn't mean that the direction that it rises and sets is changing, because Earth spins every 24 hours. That's relatively rapid. This is taking place over weeks and months. It's a much slower motion. So Mars always rises in the east and sets in the west. The reason it happens is because of the way that our line of sight changes compared to when we are overtaking the planet, when we're passing the planet in its orbit, versus at other times. So first I'll go through this, which often confuses people, and then I'll show you a video which often unconfuses people. So Earth is closer to the sun than Mars is, which means we're moving faster. Planets closer to the sun move faster in their orbits, which means we're like a faster car on a smaller track. Mars is like a slower car on a larger track. That means we're going to keep lapping Mars. We're going to keep overtaking it. About every 2 years, we catch up to and pass Mars in its orbit. And so here are corresponding positions of Earth and Mars in their orbits. So here's at time 1, here's Earth, here's Mars. I draw a line from Earth to Mars. There's where it is amongst the stars. Mars is in front of stars in Gemini at time 1 here. And then here's Earth at time 2. Here's Mars at time 2. Draw the line. Mars has moved to the east into Cancer. Time 3, draw the line. Mars is still moved further to the east in between Cancer and Leo now, although which constellations it is doesn't really matter, it's just to the east. But notice that here at 4, where we're passing Mars, it's its so-called opposition, when it and the sun are on opposite sides of our sky from one another. Now the line of sight has tipped backwards. And now Mars is at point 4. Now it's to the west of where it was at point 3. Then we get to point 5. We're still passing Mars, and it's tipped further back. Now it's at point 5 here, still to the west. But once we get ahead of Mars enough, it resumes direct motion. It seems to be going around the sun in the actual direction it's moving. Here's a video that I made at Perkins Observatory of an orrery, a device that is designed to explain this. So the representation here is, here's the sun, here's Earth, here's Mars, here's the line of sight from Earth to Mars, and the silver ball represents where Mars appears to be amongst the faraway stars. So it's a representation of that. And what you'll see as I play it is that the line of sight most of the time has Mars moving this way, but when Earth overtakes it, it goes backwards for a while, and that's the retrograde motion. So go for it. I push the button. So here Mars is moving in direct motion. The line of sight is making Mars appear to go to the east amongst the stars. But wait for it, wait for it. Earth is catching. Aha, Earth is going to pass Mars. As Earth passes Mars, the line of sight tips backwards, starts going the other direction. So Mars appeared to go backwards for a while. It's just an illusion. It's always going around the sun in the same direction, but it appears to go backwards simply because we're overtaking it. And then when we get far enough ahead of Mars, the line of sight keeps going the direction it was before, and it goes back into the so-called direct motion.
Is it because the Earth has to cover a larger distance in a smaller period of time?
Yeah, because Earth is moving faster. Earth is moving faster than Mars is. It's a consequence of Kepler's third law that the farther a planet is from the sun, the slower it's moving in its orbit. And so, as we pass Mars, it goes into retrograde motion. Yes?
How often does this happen?
So every time the planet is near what we call opposition, and how often that happens depends on how long it takes the other planet to go once around the sun. Mars takes about 2 years, 2 of our years to go once around the sun, which means that we catch up to Mars. Roughly speaking, this isn't quite right, but roughly speaking, we go around the sun twice for every one time that this Mars goes around. So, roughly speaking, after 2 years, we catch up to Mars again, and it appears to go backwards for a while before and after that point.
Did it happen in the fall?
Probably not. I think it was. I don't think it would have happened this fall because Mars was last in opposition a bit
Although
longer.
it was Mercury.
Okay,
Okay,
so
yeah, I know.
Mercury was in retrograde. I think it's in retrograde right now too.
so inferior planets like Mercury and Venus, ones close to the sun, they also undergo retrograde motion, and that's because they're orbiting between us and the sun. And the significance of them moving in retrograde motion for your life is nothing whatsoever. It doesn't matter. It has nothing to do with your life.
So Mars goes in retrograde every year?
About every 2 years.
Okay.
About every 2 years. Yeah. And it depends on the planet's orbital period. Jupiter, it's more often than that because Jupiter takes 12 years to go once around the sun. So we catch up to Jupiter about once every 13 months. And so it goes retrograde a lot more often than Mars does. Inferior planets also go retrograde because they're orbiting in between us and the sun. And so it depends on which side of their orbit they're on, whether they're appearing to move to the east or to the westernmost stars. Yes?
About why we always see the same side of the moon. How the fact that we always see the same side of the moon doesn't imply that we don't.
I can certainly do that. Let me grab a moon here. I shall be right back.
No,
All right, here's the moon. Pretend you're the Earth. Pretend you're sitting in the middle of the room. That's not what I was thinking. Pretend I didn't turn the lights off. Okay, let's try it again. Okay, so pretend you're sitting in the middle of the room. You're the Earth. Here's the lunar near side. Here's the lunar far side, the side turned away from us. Okay? So, I am the moon, I'm going to orbit the Earth. Okay, so here I go, and as the moon orbits the Earth, it always keeps the same face towards us. So it's kind of like the moon is looking at us, and it's like, Earth, you are so beautiful. I cannot take my eyes off of you. So here I've orbited around, and I have now gone halfway around the Earth, right? Gone halfway around the Earth. The same side of the moon is still facing the Earth. Just like when I was walking around you, I kept my eyes on the center of the room, always facing the same direction. have I and the moon spun on our axis compared to when we were at the front of the room? Which direction was I facing at the front of the room? I was facing the back of the room, right? Now that I'm in the back of the room, what direction? Getting all choked up about it. What direction am I facing?
Front of the room.
The front of the room. So have I spun on my axis?
No, well, yeah.
Wait a minute, if I hadn't spun on my axis, wouldn't I still be facing the
Well, you-
back of the room? If I hadn't
Yeah, you
spun at
did.
all, I would still be facing the same direction, right? But I'm not, I'm facing the front of the room now. So, here's where I was facing when I was at the front of the room. Now, I'm facing this way. Through what angle did I turn?
90. Or I mean 1.
I turned through 180, right? I made half of a rotation, 180 degrees, right? How far around its orbit did I go, or did the moon go? 180 degrees. So I spun on my axis just as much as I went around the Earth, right? If I keep going here, right? Still can't take my eyes off that beautiful Earth in the middle of the room. Here I go, okay? And now I get back to the front again. I'm facing the same direction I was before. How many degrees did I spin total? 360. How many degrees did I orbit the Earth total? 360. In other words, what's going on is not that not that the moon's not spinning on its axis. That would be this. And then you're not seeing the same face all the time. You'd be seeing the other side of the moon when it was halfway around the orbit. No, what is happening is the moon is spinning on its axis with the same period that it orbits the Earth. It's spinning on its axis at the same rate that it's orbiting the Earth, keeping them locked to one another. It's not perfect because the moon's orbit is elliptical, and so sometimes it's moving faster in its orbit, sometimes it's moving slower in its orbit, which means we actually get to see a little bit more than half the moon over the course of the month, because sometimes it's spinning faster than it's orbiting, and sometimes it's spinning, well, I should put it this way, sometimes it's orbiting faster than it's spinning, and sometimes it's orbiting slower than it's spinning, which means that it doesn't exactly keep the same face towards us. In fact, what happens is it appears to nod its head a little bit in what is called the lunar libration. And so we can actually see a little bit more than half of the moon's surface. And that's what this is illustrating. This is an illustration of a lunation, a full cycle of phases. And so the moon appears to kind of nod its head back and forth because it's only in an average sense that it spins and orbits at the same rate. So we actually can see about 59% of the moon's surface overall as a result of that. And I'm going to make this stop because it can make people sick sometimes. So.
How many multiple choice in short answer?
I would say that there are approximately 38 multiple choice and approximately 6 short answers.
Okay.
And that's it, like, is there anything else?
No.
Is there anything people want to tell us?
Yeah.
Benefit us tomorrow?
Good.
Wow.
That's great.
No, the moon phases.
Yes, no, the moon
And like
phase.
the time.
Yes, I mean, I have told you some things, right? So, so I guaranteed you that there would be a question along the lines where you're going to tell me the difference between the everyday meaning of factor theory and the scientific meaning of factor theory.
Yeah.
Yes.
That's what I was in the homework I was due last night.
Yeah,
Okay.
yeah, and in my PowerPoint, my
Yeah.
Google slides where I was talking about Senator Barbara Lawrence of Kansas and all this kind of stuff. So be able to go through that. Another thing is I guaranteed you that you will see things from the packet on the moon phases. So in other words, that moon phase wheel, all that kind
Is
of
that
stuff.
on Blackboard? Or
It is,
okay,
it is, and I handed it out in
Yeah,
class.
I saw that one.
And there was 12 of them for you to do, and I gave you the answers, but not the solutions. And you need to be able to do that. You need to be able to explain in words how you figured out that the direction to the waxing crescent moon that you were seeing at 4 in the morning, or at 4 p.m. was what, or whatever, or to draw a moon phase wheel to explain.
Okay.
that. Yeah.
Okay.
Mhm.
Oh,
Did I say something about what?
Barbara?
Barbara?
Oh, no, I just heard, never mind.
Well, I mean, my colleague Barbara,
Oh, that was it, okay, let's do this.
Barbara Andrick developed that 3D moon phase exercise, the one that I had to do for extra credit. But I don't think I said that just now, unless it was like, I have this liminal thing going in my head or something like that. You look like you were about to ask a question.
The fact and theory, it was like scientific versus just normal.
Yeah, so remember that in everyday English, a theory is a guess that can turn into a fact when you get enough evidence for it. In science, facts are things we observe to be true about the natural world, like the Earth goes around the sun, the Earth spins once a day, and so forth. Theories are explanations of facts in science. So the theory of evolution explains our observations that show that life forms evolve over time, change their genomes over time. The theory of evolution explains how that occurs. So in other words, the theory of evolution isn't just, we're guessing about evolution, we haven't proven it yet. No, there's lots of observations that have demonstrated that evolution is something that occurs. The theory of evolution by natural selection is an explanation of the mechanism of evolution. It's not the only way that evolution occurs. There's also things called like genetic drift and so forth. But natural selection plays a role, a very important role in causing species to change over time. So in other words, theories in science are explanations of the whys behind facts.
Have a great night.
Good night.
Thank you so much.
Yep, you're welcome.
Will there be any on the homework there was like what can be falsifiable and what?
Yeah, there could be things like that, right? Like
Okay.
anything like that, you could be asked to apply what we've learned, like into the style of mastering astronomy kind of stuff.
Okay, so I just probably look through that.
Yeah. I mean, obviously, I can't write, I can't ask you everything, but it's all
Yeah.
up for grabs.
Okay.
There's two reasons for exams. One is evaluative, right? One is see how well you're doing from the professor's standpoint. But the other is to get you to study for it, right? And so I can't possibly ask you everything, but it's motivation to try to study as much as you can and learn as much as you can.
Right.
Yep.
Thank you.
You're welcome. I will see you tomorrow.
Yep. Will we get the class period, or is there like a time?
You get the class period,
Okay.
basically, yeah. But it should be enough. It
Yeah.
should be